All right, so we've already discussed number sets. The following sets of numbers are subsets of the set of reals. So we already began to look at the real number line. All right, so we discussed the natural numbers. We said that they would start with 1. So 1, 2, 3, dot, dot, dot. That's the ellipsis. So 1 on out, no fractions, no decimals, just your whole numbers, 1 and above. Your whole numbers are those 0, 1, 2, and 3. I made a little reminder here, and I think I misspoke the other day in class and said the Middle Ages. I actually Googled it. The earliest records of 0 are Babylonian and Mayan civilizations, but they didn't necessarily use the symbol 0 that we know today. But there's a lot of debate about when 0 came onto the scene in terms of the evolution of mathematics. So your whole numbers begin with 0, and then 1, 2, 3, dot, 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 on out. Still no fractions, still no decimals. Your integers are your negative and positive whole numbers, including 0. Your rationals are any number of the form p over q, such that p and q are integers, and q is not equal to 0. And your irrationals are any number that cannot be written in fraction form, such as pi and e. So let's just kind of see what let's test your memory here. We drew these bubbles before in class. Is anybody, something like that? These are actually subsets. What's the smallest one? Good. And then? Integers, good. And then? Yeah, rational. Yep. And then who's over here? Yeah, see, those of you with a photographic memory, this will burn into your head and you'll have it. Yeah. Okay. And this? And reals. Very good. So now, this might help us with the following question. Let's just make sure we're catching it here. All right. To which set or sets of numbers does -1 belong? So it's definitely an integer. Is it whole? No. Okay. Yep. Is -1 rational? Okay, good. Is it irrational? Oh, you can't be rational and irrational at the same time, right? So it's an integer, it's rational, and of course it is, real. Yeah. So obviously all of these belong to the set of reals. All of these here. So a question did come up. If all of these belong to the set of reals, then perhaps there's another set of numbers out here called imaginary numbers, which we're going to deal with next semester. But what do they look like? Does anybody know? Yeah. Well, you mean, like, for example?
N doesn't actually mean anything, but it's actually 1 n or something.
Well, I'll give you a good building block here. What happened to mathematicians is they knew the square root of 1 was 1. So they said, aha, what about the square root of -1? Oh, and that's the fundamental building block of the entire imaginary number system, is that I is the square root of -1. We, at a point in our history, we did not have a way of dealing with the square root of negative numbers. And at a point in our history, we did not think that there was an application for the square root of negative numbers. And now mankind is far enough along to know that electric circuit theory, electromagnetism, cartography, many things need the square root of negative numbers. So what we did was we developed an entire number system called the imaginary number system, based off of the fact that I is the square root of -1. We'll go more deeply into that next semester. Give it a shot. All right, so in the next example, we're going to write the set of integers greater than -2.1 and less than 3/4. Now I'm going to give you a little push. When you write a set, what do you need in terms of set notation? What are these? What are these? Curly braces, yeah. So the first thing we say is curly braces. So when you think about set of numbers, curly braces. A list of numbers separated by commas. Okay, well, what are the keyword integers? What are the integers that are greater than -2.1 but simultaneously less than 3/4?
-1, 0.
I like -2. I like -1. I like 0. And I'm going to play devil's advocate. How come you didn't pick 1?
Because 3/4 is less than 1.
Good. So some of you may even have to picture the real number line in your head. Like here's -2, here's -3, especially if you're a visual person. And just think about where are all the integers that are greater than -2.1. So here's -2.1. So we're looking at, here's an integer, here's an integer, here's an integer, but we can't take 1 because that's not less than 3/4. Okay? So you just really have to think about where you're going to start and where you're going to stop. Okay? Let's mess with this language here a little bit. What if it said, what if I took out the word integers here, and what if I said whole? Little sidebar here. What if we wanted to write the set of whole numbers greater than -2.1 and less than 3/4? You said that would only be, that set would only contain 0. But what if I changed the word integers to naturals? So sort of like, what if I wiped out this word and changed it to naturals? Write the set of naturals greater than -2.1 and less than 3/4. What would? Yeah, yeah. Well, that's the thing. Are there any natural numbers that are greater than -2.1 and less than 3/4? Right, and that's called the null set. If you've seen this, by the way, null set means the set that contains nothing. It's not a 0. It means the empty set or the null set. It means the set that contains nothing. A lot of people write their zeros that way, and some teachers mark them off because that's not a 0. That's the null set. Okay, so skill set, fractions. 4/9 and 7/6. The author wants us to find the LCD and add the fractions. I like to think of as we build these skill sets, these are things that people often make silly errors on a test, so we're just fine-tuning here. Finding the LCD shouldn't be a problem. What do you think? I heard 18 initially. Now, if you're not sure about how to find an LCD, you could do a prime tree, or and when the numbers are small like this, a nice technique would be to just look at multiples of 9. So note to self: if you look at multiples of 9 until you hit something that 6 goes into, so 9 and then 18. Right? So you'll hit it pretty quickly, and you quickly realize that 6 will go into 18 as well. So you found a number that both 9 and 6 go into, okay? So 18 is the LCD. 4/9 is equivalent to blank.
It just comes up on the 2.
Exactly. So is equivalent to blank over 18.
No, I was just saying for the LCD.
Yeah, well, to get the to identify an LCD, you would take multiples of the larger number. So multiples of 9, 18, 27, until you hit something that 6 goes into as well. So like, can I pick 27 as the LCD? No, because 6 doesn't go into 27. But can I pick 18 as the LCD? Yes, because 6 divides into 18. Now, if that don't work for you, the only other thing you could do is this, because I know there's different strokes for different folks. You could do a prime tree for 6. You could do a prime tree for 9. And you could use the recipe we talked about that says to take the most amount of 3s that anybody has, which is 2 of them, and the most amount of 2s that anybody has, which is 1 of them. And you could literally write a prescription for the LCD. So the LCD would be 3.3.2, which is still 18. But that's a little more tedious than just taking multiples of 9, like 9, 18, 27. So you'll hit 18 pretty quick as your LCD. I'm going to play devil's advocate. How comes 9 times 6, which is 54, how come 54 isn't the LCD? It's not the least, yeah, it's a common denominator, and you could use it, but you'd get stuck reducing at the end. So these are excellent questions, guys. Okay, so let's see if I can get you to say that. So 4/9 is equivalent to something out of 18. Good. And 7/6 is equivalent to something out of 18. Good, 21. And if you're wondering how that happened, all you have to do is say, how does 6 become 18? Times by 3. So if you're going to multiply the bottom by 3, to keep it legal, you got to multiply the top by 3, and that's how you're going to arrive at 21 over 18. So then we can go ahead and add those. So 8 plus 21 is 29, And we got 29 over 18. No need to convert that to a mixed number. Can if you feel like it, but it's not necessary. Reductions or putting in lowest terms is another useful skill with fractions. We talked about, at the board yesterday, we talked about how to reduce them mentally or physically with a prime tree. Now, just out of curiosity, who would like to make prime trees for 42 and 91? Okay, well, let's go that way. Some people will try to reduce that mentally, but maybe a prime tree is useful sometimes. What's the prime tree for 42? What times what makes 42?
7 times 6.
All right, is 7 prime?
Yes.
All right, 6 breaks into?
2 and 3.
All right, so we'll circle those because they're prime. Now we've got a prime tree for 91. Well, what times what makes 91?
7 times 13.
Ah, now here's a trick. If you didn't know that off the top of your head, like if you're going through numbers in your head, like, man, I can't find something that goes into 91. If 2 doesn't work and 3 doesn't work, chances are it may be another prime number that exists between 1 and 10. What other prime number could we find? 5, but 5 definitely doesn't work. Maybe 7. So always try prime numbers. If nothing comes to the top of your head, it might be a prime number. In fact, both of these guys are prime, right? So now we'll write the prime factorization of 42, which is 2 times 3 times 7. Prime factorization of 91, which is 7 times 13. And what are the common factors? Yep, so we'll wipe those out because anything divided by itself is 1. What's really happening there is you're getting a 1. So 2 times 3 is? And you're left with 13. Good, so we have 6/13. If you had a calculator, what you could do, which is a great thing to check, is if you don't believe yourself that you did it right, check the decimals. Hit 42 over 91 and verify that the decimal for 42 over 91 is the same decimal for 6 over 13. If you get the same decimal equivalent, you know you did it right. Okay, next example is on a label. A label on the back of a fish stick says that a serving size is 250 calories and 130 are coming from fat. What percent of those calories are coming from fat? So the first thing you think of is fraction. Let's practice going, I like to call it FDP, from fraction to decimal to percent, the old-fashioned way. So, all right, 130 out of 250. Let's practice what? So that's going to reduce down to, all right, so that's going to reduce down to 13 out of 25. So that's what fraction comes from fat. Now, how do you get that to be a percent if you're going to go the old-fashioned way? Yep.
What you're going to do is that's
Yeah.
25 could be 100,
Ooh,
well,
no.
not 140, I mean, what I did was I multiplied 25 by 4, which is 100, which out of 100.
Oh, that's a slick way.
I got 22%.
Ooh, that's a slick way. So you're saying, gee, luckily 25 goes into 100.
That's only the number can be multiplied equals.
Right, right. And I was going to, yeah, so you might look at that and say, gee, I could multiply this by 4 and multiply this by 4 and arrive at, yeah, and then you know that inherently that's 52%. That's a neat way of doing it. Now, what if you wanted to go what I like to call FDP, from fraction to decimal to percent? Then what would you have to do?
Yeah, divide 13 by 25 and multiply by 100.
Right, very good. So you physically take 25 into 13.0, and if it's been a while since you've done that, what do you do with that decimal? Line it up. I know a lot of people get rusty with good old-fashioned division. 5 times 5 is 25. Okay, and look for the remainder, and there you go. So how do you move from 0.52 to 52%? Like you said, you could multiply by 100, or some people say you're just going to slide that decimal 2 to the right, and you'll arrive at 52%. So 0.52 to 52%, there's, like you said, there's lots of ways to get there. All right, so last skill set here that we want to practice is properties of algebra and working with signed numbers. Now, can anybody, just out of curiosity, can anybody recite at least 4 properties of algebra?
Is it addition, subtraction, multiplication, division?
Well, I'll give you a hint. Those are operations. How about commutative? There. Okay. Commutative. Good. Associative. associative, additive inverse. Let's keep going. Additive inverse. How about multiplicative inverse? Okay, that's exactly. When it becomes new, that's when you hold fast. Okay. Okay, so we'll add to that list properties of 0 and 1. So there's no fancy name for that, just other than properties of 0 and 1. Okay, well, let's start off with commutative. And a question came up, it was a good question, how about the identity properties? They involve 0 and 1, but they are important. Yes, so let's add those to the list, identity properties. Okay? Let's go one by one. Commutative, let's see if you believe this. Do you believe that A plus B is equal to B plus A? All right, how come? Because 7 plus 3 equals 3 plus 7, right? So there you have yourself what's called the commutative property of addition. Okay, do you believe, anytime we have a property, I'm going to put it in a box, do you believe that A dot B equals B dot A? That A times B equals B times A? Because 7 times 4 is yields the same thing as 4 times 7, right? That's called the commutative property. So notice that this holds for addition and it holds for multiplication. Okay? But it doesn't hold true for subtraction, and it doesn't hold true for division. So it only holds true for addition and multiplication. Okay, that seems believable. Now this may not seem as believable. Let's look at associativity. Associative properties. Okay? Do you believe that A plus B plus C is equal to A plus B plus C if I change the grouping? And sometimes that doesn't seem believable, so what I always say is put some numbers in there. Is 5 plus 3 plus 4 with this grouped off the same thing as 5 plus 3 plus 4 with this grouped off? Well, let's investigate. Well, that's 8 plus 4, and over here I'd get 7 plus 5, and does that yield the same thing? Well, yeah, 12 equals 12. So the associative property of addition may not look true, but it is. And you have to investigate that. And it turns out that I could change that plus sign to, so I'm going to put that in the box, I could change that plus sign to a dot, meaning it holds true for multiplication as well. So A dot B dot C is equal to A dot B dot C, and I can group these guys off, and I will yield the same result. Okay, so it's legal for addition. And so big note to self over here, holds true for addition and multiplication. So holds true for addition and multiplication. Not for division and subtraction. The next one is going to be the distributive property. Let's zoom in on that. You may be recalling that says that A times B plus C is mathematically equivalent to, anybody? Yeah, A times B plus, yeah, and if that doesn't seem intuitive, put numbers in there. See if it's true. I always tell people, see if it's true. 7 parentheses 3 plus 4. Is it true that that's equal to 7 times 3 plus 7 times 4? Well, let's see it. Let's try it. So if we do that, we'll get 21 plus 28, which is 49. But and you say, well, how do you know that that's true? Well, what if you didn't use the distributive property? What if you just did these two numbers and added them? Well, 3 plus 4 is 7, but hey, 7 times 7 is, yeah. So whether you use the distributive property or not, you're still going to arrive at 49. That's kind of what that says. So meaning if you just added these two together first and then times by 7, you're still going to arrive at 49. Or if you use the distributive property. Okay, inverse properties real quick. Anything plus its additive inverse, so A plus negative A, will bring you to? Right. So anything plus its additive inverse will bring you to 0. That's your additive inverse. Your multiplicative inverse is that anything times its something will bring you to 1. A times what will bring you to 1? Yeah, but what is the multiplicative inverse of A? Just think about A times what makes 1. It's a little tricky.
What is the fraction? Whatever the fraction is of that number.
How about 1 over A? Right? And there's a word for that. Yeah, so anything times its reciprocal sends you to 1. Think about that. 1,000 times 1 over 1,000 is 1. That's right. So again, that's your additive inverse. And that's your multiplicative. I'm going to abbreviate. It's a long word. Multiplicative inverse. That's right. So anything times its reciprocal brings you to 1. Anything plus its additive inverse brings you to 0. Okay. Okay, how about this? Anything plus 0 equals, anything plus 0. Yeah, anything plus 0 equals itself. Yeah, that's what's called the additive identity. And so, you know, a lot of people say, man, there's so many words. I know. There's a lot of words, but it's things that we've known for a long time. And anything times 1 equals itself, exactly. We've known that for a long time. And that's the multiplicative identity. So that's your multiplicative identity property. Okay, so you've got your properties. Some textbooks go into this. I'm going to go into it. Additional properties that you should think about are the properties of 0 and 1, like we had mentioned earlier. So let's take a quick look at those. I'm going to extend page. It's going to get, I'll put another page up. I can go back, any page you want, I can go back to then. So this is going to be your properties. I'm just going to list them. Important properties of 0 and 1. These are kind of like additional. And we mentioned it before. Anything over 0 is good. And a lot of people say under the line is undefined. 0 under the line is undefined. That's right. But 0 over anything is 0. That's right. And anything over itself is 1. Good. And anything over 1 is is itself. That's right. So A over 1 is A.